So what we're going to be talking about here in section 2 is calculating lengths within these three-dimensional solids. So in most of these cases, the trick, the hardest part, and really the hardest part, I think, of this whole chapter is going to be finding these appropriate calculation triangles. So more often than not, what we're going to be wanting to do is we're going to want to find a right triangle that's inside of the three-dimensional figure that we're talking about that contains, the information that we're looking to solve for. So there's lots of possible calculation triangles. So for example, if we take this pyramid here, this triangle in pink is an example of a calculation triangle. Now there's lots of triangles that are calculation triangles, that are right triangles. And in fact, this particular calculation triangle is not even unique, right? It should be fairly easy to see that there's 4 of these triangles that are exactly the same size as this triangle ABC. One going here, one here, and then one kind of over there. Do you guys see that? But there's other right triangles in this as well. Another right triangle would be, instead of going where this side AB is going to where B is the midpoint of this side, if AB is this side where we're going to the edge or the corner of our square, that makes another calculation triangle. It is also a right triangle. It's a little bit harder to see that it's a right triangle from the picture, but it is, and that's maybe some of the more challenging part of this, is that you really have to be able to visualize something in 3 dimensions, because the 2-dimensional projection on a sheet of paper doesn't always give you a great picture of kind of what's at a right angle and what's not. And then another possible calculation triangle here would be like, we're still using CB, but here A would be at the corner. So if we look at half of one of these triangular faces for our pyramid, that's also a right triangle and another possible calculation triangle. So really kind of the hardest part of this becomes finding those calculation triangles and being able to figure out which of the calculation triangles we need in order to kind of solve the problem that we're looking to solve. Okay, so like I had mentioned, that sometimes it's easy to see these calculation triangles, and sometimes it's not. So this pink one here, where it's just half of that front face of our cube, cuboid is just another term for a cube. That should be fairly easy to see that that's a right triangle. But this triangle in blue is also a right triangle, a little bit less obvious. So FG is like this edge on the top of the cube. GD is the diagonal across that face. And then DF is this internal diagonal going through the center of the cube. Now we know that this is a right triangle because I know the faces of our cube are intersecting at a right angle. So the face FBCG intersects the face GHDC at a right angle. And since FG is on that face and GD is on the other face, they must also be intersecting at a right angle. So this angle FGD is our right angle in that other triangle. Is everybody okay with that idea? Again, if you're able to kind of close your eyes and visualize what's going on, it's helpful. And I know that's, the ease in which we're able to do that is going to vary individual by individual, because you don't get a lot of specific practice kind of doing that. And some of us have some natural inclination to being good at spatial reasoning and be able to see those things in 3 dimension in our mind's eye. And some of us might struggle with that. And that's, again, like, it's okay. Practice will kind of flatten that curve for us a little bit. But if you're one that like really kind of struggles to see those relationships, you really want to make sure you spend some time and kind of slow down and practice kind of visualizing it in your head until you can see it. And that'll really kind of help speed things up for you. Continuing on, just looking at some more of these unexpected situations. So here is a triangular prism. So when we talk about a prism, what we're talking about is we should have 2 parallel bases. So in this case, our basis for our prism is this triangle ABC and this triangle DEF. And then the faces connecting those bases should be all rectangles. So this guy is a prism because it's got 2 triangles connected by a bunch of rectangles. Everybody's okay with that idea? If you had that cuboid before, it could be technically called a square prism, where you have 2 squares that are connected by rectangles, because squares are rectangles from a definition standpoint. And you can have, obviously, lots of other kinds of prisms, and typically we name the prism by the shape of its base. Okay, so the pink triangle, pretty obvious that that's going to be a right triangle, right? It looks like a right triangle, no surprise there. This blue triangle, EBG, is also a right triangle. So EB is that edge along the apex. BG is the height of the triangular base. And GC is like this internal diagonal that's going from the midpoint of AC through the inside of our prism to this other point E. So again, we know that this is a right angle or right triangle because the height of our triangle needs to intersect this top edge of our face at a 90-degree angle. So this angle GBE is our right angle. And again, looking at the picture, doesn't necessarily look like a right triangle, but when you think about it in 3 dimensions, it's much easier to see that, oh yeah, okay, that has to be a right triangle because the bases of my prism are exactly the same size or whatever. Everybody okay there? Okay. Looking at some more. So the blue triangle, again, should be fairly easy to see that that's a right triangle. It looks like a right triangle. EFM is the right angle. The pink triangle is also a right triangle that doesn't look at all like a right triangle. But we know the height of a pyramid is going to intersect the base at a 90-degree angle. So any other side that's like inside the plane of the base also has to be intersecting at a right angle. So this angle AFE is also a right angle. And again, if you think about that in your mind's eye, it's like, oh yeah, of course, definitely doesn't matter. Like if I have something sticking straight up, what, like whether I have it coming out here, here, or here, like it's still making a right angle, right? The reason it doesn't look like a right angle is because you're projecting a 3-dimensional object into a 2-dimensional space. So you get a little distortion. It's like when you look at a map and Greenland looks enormous when you know Greenland's really not that big of a landmass. It's the same kind of distortion. Okay. So let's do some examples here now. So here, this first example says that we have a shoebox that's 32 by 18 by 11. And we want to find the length of the longest rod that'll fit inside the box. So to do that, let's kind of come up with a plan here. I would start by sketching a picture. And then we need to identify the calculation triangle we need to solve our question. And then sketch and label that calculation triangle and then solve for the desired piece of it. Is kind of what I'm going to do. The most difficult part is going to be identify the calculation triangle we need. So think about like a shoebox size. Okay, so like a rectangular prism. What's going to be how would you be able to put like the longest thing possible inside of that? How would that have to go? So you have like some box. When you say diagonal, what do you mean?
The top left corner, the bottom right.
Excellent. So like an internal diagonal, not like necessarily a diagonal on the face, but like from the top upper left to the bottom lower right or something like that. Good. So let's go ahead and draw our picture. So here's a picture of my box. And then the calculation triangle I need is going to involve a piece going from F to D, or from G to A, or from E to C, something like that, right? So this is the one the calculation triangle that I drew. So I used AG. So I needed GC then as well, and then AC. And it didn't really matter which one of those four possible calculation triangles you drew. This one to me was the easiest one for me to like fit on my diagram. That's why I kind of put it there, but there's no real reason it needs to be there. Now, if we think about our calculation triangle, we're looking for the side AG. We know the side GC because that's a height, but we don't know AC yet. Everybody agree with that? In order to find AG, we just need to figure out what AC is, and then we can use the Pythagorean theorem. How can I find AC? Go ahead.
Okay, well, there's another right triangle on the bottom. So you do 32 squared, 8 squared.
Yeah, so we'll just make a second calculation triangle that involves AC, and hopefully it's a triangle that we know both of the other sides for. So that's exactly right. So we'll do that. So when we calculate that, we get that AC is the square root of 1348. And now we can solve AGC. So 1348, or square root of 1348 is 36.7. That's where that number comes from. And now we can just do the Pythagorean theorem again, and we get AG is the square root of 1469, or about 38.33. And this is a pretty like medium to hard level problem, particularly if we didn't give you the picture to begin with, right? So I would say it's medium hard because you have to use two separate calculation triangles, and then maybe it's not totally obvious at first what even piece of the box you're having to solve for, where that longest rod possible is going to go. Now, if you think about it in 3 dimensions for a minute, it should become pretty clear what that would be, but it's maybe not always obvious right from the get-go. Everybody's okay so far? We'll go and do another example. So let's say we have EABCD is a square-based right pyramid where the sides of the square are 12 and the height of the pyramid is 9.5. We're going to calculate the length of EC, and then at a point M, that's the midpoint along one side of the base, we're going to calculate the length of EM, and then discuss why EC and EM are not the same length. So just like before, we'll start by drawing ourselves a picture and kind of labeling our information. So when we name a pyramid with just 5 letters like this, typically the first letter is the apex of the pyramid. Is kind of the convention that we use when naming like a figure like that. And I drew my calculation triangle here for EC as follows. I drew this particular one because it involved the height of the pyramid, which I knew was 9.5, but I don't know this side FC. Again, we're looking for EC. So what am I going to have to do to find the length of FC? Jacob?
Can you just like then use it to 12 or change it 12 to us like 6, like make a right triangle right there, and the other side would be 6 too.
So Jacob's saying like I can do this, which turns that into a 6 and this into a 6. That is okay to do. Yep. Why do you know that this one is 6?
Because it's like half the whole side.
Yeah, so AD is 12. F is because this is a right pyramid, the altitude or the height of that pyramid is going to land right in the middle of the base. So F is like, if we project F to any of these sides at a right angle, it's going to be a midpoint on the other side. And that's fine. You could certainly do that. I don't think that's the most obvious one to do, but that works, and there's nothing wrong with doing that. I would do that, but it's a PowerPoint, and I've pre-planned already what I'm going to do, so I used a different calculation triangle. Rather, what I did was I used ADC, and then calculated the length of AC and divided it in 2, which is equivalent to what Jacob's doing. It's going to get you the exact same answer. I just think it's a little bit easier to do that. So I did that. Again, I know that F is the midpoint of AC because this is a right pyramid. If the pyramid wasn't straight up and down, if it was like tilting somehow, that would no longer be true, but you won't see a situation like that in this class. But it's worth pointing out that that's the reason that F is like the midpoint there is because you're working with a right pyramid, that it's straight up and down. Now, if you had like a leaning Tower of Pisa situation with your pyramid, now that's no longer the case. All right, so we have our length for AC. We can divide that in 2 to get FC. And now that we have our length for FC, we can go back and find EC. Oops. Come on. Oh my gosh, you are so laggy. I hate you so much, computer. Okay. Again, are we okay with that? Now there's some more parts to this question. This was just part. Part B says at a point M marked halfway along one of the sides. So here's my point M. That's a midpoint here. We're going to calculate the length of EM. So EF is still 9.5, and as Jacob argued earlier, this piece has to be half of 12, or 6, and then it's easy to find the length for EM. So which one did we notice was longer, EC or EM? EC was longer. Let's think about why EC has to be longer than EM. This, you could have made this argument before we actually even solved anything. Ben? Okay. So here's the best argument. Consider the triangle EMC. What kind of triangle is that? It's a right triangle. EC is the hypotenuse, which has to be the longest side in a right triangle. So EC necessarily must be longer than EM. They cannot be the same length. Everybody feel okay with that argument? That's the best argument because it doesn't require even to know what the lengths are, or to make some like, well, this one is like at a diagonal and this one's kind of going flat, you know, like you don't have to try to make that kind of an argument either. It's a purely one triangle argument, which is pretty convincing, right? So that was our explanation for why they cannot be the same length. Obviously, they're pieces of two separate triangles, but all right. I think we have one more example here. This is our last one. So let's say that we have this cone where the edge length of our cone is 11.3. And the apex angle of our cone is 53, so we're talking about this angle up here. And we want to calculate the radius of the cone. So I've gone ahead and drawn a calculation triangle. Now we know this side is 11.3. Well, that's the only piece of information we're given. Other than this angle, what are we going to have to use to calculate this value for R? Ben?
So I'm not sure about this, but since it's looking at the radius, it will be 53 by 2.
Okay.
You could then figure out the angle because it's 90 degrees. It will be a 90 degrees. So angle C would be 180 minus 90 minus 1. You'll be able to find the other side length with the loss or what goes out.
Yeah, you could do SOHCAHTOA, right? You do right angle trigonometry because you're inside of a right triangle. Good. So one little detail that I'd like to kind of clarify is we took this angle, this 53-degree angle, and we made the assumption that BD bisects it, right? That it's going to cut that angle in half, which is true in this case, but it doesn't always have to be true. What is special about this situation that guarantees that BD is going to bisect that angle? Not necessarily that it's a right, when you say right triangle, you're talking about the shaded triangle here? Not necessarily. Not necessarily. I could draw a cone where this doesn't happen. So consider the triangle ABC. What's special about that triangle? It's not equilateral, but it is isosceles. And we know that the altitude of an isosceles triangle bisects that apex angle, and it bisects the base of the triangle. That was a theorem from geometry. Now, I don't expect you to remember that theorem per se right away, but that's the key as to why that 53 gets bisected, is because it must be an isosceles triangle. And we've run into problems like that on previous tests where we had like two people looking at the same thing, but it wasn't an isosceles triangle, and people are trying to like drop an altitude and divide the base in half. You guys remember a problem similar to that? I think it was on a test. It might have even been a test question from a previous test where several people were like, oh, just drop an altitude, divide this base in half, a right triangle. And it's like, nope. You don't have an isosceles triangle. So that part is important. So I just want to make sure that I hit on that, because I've seen some of us make that assumption incorrectly, that things are just going to get bisected. Really, you need that isosceles triangle in order to guarantee that kind of thing. Okay. So there's my right triangle. And now we can just use, in this case, I would use sine, because I'm looking for the opposite and I know the hypotenuse, to calculate r. All right. Question for you guys. Would you prefer to do 2 lessons today or 2 lessons next time? It doesn't really matter to me. Whatever you want to do, it's fine with me. It's not like it's going to change what's due on Sunday or whatever. Today? Okay. That's fine. I just, just trying to be, give you some say, right? Act like that we're being accommodating or whatever. Oh my goodness, what just happened? Yes. 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 Okay. Next up, we're going to be talking about angles within 3D solids. So not substantively different than what we've just been working on, except instead of looking for lengths all the time, we'll be looking for angles here. Again, we're going to be mostly looking for calculation triangles. Now, with angle searches, you might also be able to use like a non-right triangle, but you'd be forced to use like the law of sines or cosines, which again, not a big deal that you might have to break that out, but like usually there's a way to do it with just right triangles. It's, I think, a little bit simpler calculation-wise, and that's usually my preference, but it's worth noting that you could get away with that in many situations. So when we talk about an angle in solid, what we're often talking about is the angle that that a side makes when intersecting a plane. So if we talk about like this angle AB or this line AB intersecting this plane, we're talking about like an angle here where the other side of our other arm of our angle is just some segment inside of the plane. Is everybody okay with that notion? So we might be asked about angle ABC, which is the angle between the base of the cone and this slant edge. So it's talking about this angle here. Angle ACB is the angle between this height of the pyramid and this edge. So we have AC and CB. And then here, FAC is the angle between this edge AF. Oh, I'm sorry, that's an internal diagonal AF. No, that's the diagonal of the face. This is like a doorstop is what this shape looks like. It's like a wedge. So AF is the diagonal on the top of the wedge, and AC is the diagonal on the base of the wedge. Can you guys kind of visualize that now after we sort that out? So let's do a couple of examples here. So for this triangular prism, another wedge here, we're going to find the height EB. We're going to find the length DB, and then the length DE, so all three sides of this triangle here. And then the angle that DE forms with the base of the prism. So this angle DEB will be the last piece. Everybody okay there? Okay. So EB is the first up. So I'm just going to take this right triangle here, AEB. I know that this side is 15 because this side was also 15. And I'm given this 21-degree angle. So I can just use tangent to calculate EB. Everybody good with that? Next up, we want that length of the line DB. So this is basically the bottom of this wedge. So again, these are right triangles, so I can just use the Pythagorean theorem to find DB. And the next up is looking for DE. Since I know DB and I know EB, I can just use the Pythagorean theorem to find DE. So far, so good. And then since I know all three sides of this right triangle, I could use any sine, cosine, or tangent to solve for that angle measure. I just have to arrange the side lengths in the appropriate manner. So I'm going to use tangent and use my answers for the first two parts. But since we know all three sides, you could have used any trig function. So that angle is going to be tangent inverse of opposite over adjacent, which comes out to be about 11.84. Krista? Absolutely. Oops. Next question, or next example. A cylindrical drum contains a stick that fits the diagonal exactly. The radius of the drum is 5.8, and the height is 15.8. Calculate the length of the stick, and then the angle that the stick makes with the side of the drum. So the calculation triangle to find the length of the stick, well, let's just use like ABC here. Now, BC, clearly we know. What is the length of AC gotta be? Yeah, 5.8 times 2, right? Because it's a diameter. And then we can just use the Pythagorean theorem to find the length of our stick. To find the angle the stick makes with the side of the drum, which angle am I looking for? BAC or ABC? So it wants the side of the drum, so that's ABC. Everybody agree with that? Because that's the angle of the stick and the side of the drum is this one right here. So I can, if I know these two sides, again, I know AB, so I could really use any three of the trig functions, but I know these two exactly, so I'm going to use tangent. So that angle ABC is going to be tangent inverse of opposite over adjacent. Everybody cool? No big deal? Look at this photo of art. A rescue helicopter is hovering 156 meters above the sea. It is dark, and the helicopter is shining a light down onto the surface of the sea. If the diameter of the cone formed by the beam of light is 140 meters, what is the angle at the apex of the cone? So here's our cone of light. It's 156 meters to the ocean here. And the diameter, LO, is 140 meters. And we're looking for this. So we'll just make a right triangle here. Calculate that angle at the apex and then multiply it by 2 to get the whole thing. Everybody sound good there? How do I know that this little pink part is half of the whole angle? It's an isosceles triangle. Yes, good. You guys were paying attention. Yes. All right. So we know these two pieces. How did I know this was 70? Yeah, half the diameter. So we can use tangent inverse of opposite over adjacent to get that. And then our whole angle is just twice that result. So far, so good. That was it. Awesome, right? I know, I'm thrilled too. We'll stop here. You guys should be able to do 1 through 15 in the homework set after that. So you guys can start on that. And we'll let you guys work till the end of the hour, the next 30 minutes or so. With any luck, you can probably finish the whole thing. Or maybe not. You know, I don't want to put that kind of pressure on you. You finish some of it, though. Those of us working from home, you guys are free to end the Zoom call if you'd like. You can stay on, obviously. No big deal. It'll still be there. But if you'd prefer to move and work someplace more comfortable, all we're going to be doing is just working on the assignment.